Now for one that's a little bit more of a challenge, we're going to test for convergence the sum from n equals 1 to infinity of the tangent of 1 over n. Now when we consider what the graph of the tangent function looks like, we need to consider what happens when n is getting very, very big. Now when n gets very, very big, this thing gets very, very small. 1 over n is essentially going to go to 0. The graph of the tangent function, if we were to take a look at it really close to x equals 0, we can actually approximate this thing really well by using the slope of the tangent line to the tangent curve. Boy, tangent line to the tangent curve, what a time to be alive. So if we consider y equals the tangent of x at x equals 0, the slope of the tangent line at x equals 0 is going to be the secant squared of 0, which is 1. Given that it passes through the origin, we would want a line of slope 1 passing through the origin. So what I'm saying is, when the inside gets really, really small, or really close to 0, it's essentially going to be behaving the same as whatever's on the inside. So the tangent of x is going to start acting like x. So the tangent of 1 over n is going to start acting like 1 over n. Now, what we're going to do here will be a limit comparison test. So with that in mind, one big important thing to keep in mind is that this would be considered the harmonic series, which diverges for a number of reasons. Integral test, p-series test, all sorts of good stuff. So for the limit comparison test, what we need to show is that the limit as n goes to infinity of the ratio of the terms of these sequences is going to be both finite as well as non-zero. So with that in mind, in its current state, if we allow n to go to infinity, this goes to 0, tangent of 0 is 0. This goes to 0 as well. L'Hopital's rule is applicable here. So this will be the limit as n goes to infinity of, differentiating the top, we'll get the secant squared of 1 over n times the derivative of 1 over n. In your denominator, we will have the derivative of 1 over n. I don't even care about the fact that that derivative happens to be equal to negative 1 over n squared, because they're going to cancel out anyway. This gives me the limit as n goes to infinity of the secant squared of 1 over n. This would be the secant squared of 0, which, as we just mentioned, that's equal to 1. Now, because we got something that is both finite as well as non-zero, we are allowed to draw a conclusion using the limit comparison test. Therefore, by the limit comparison test, the series sum from n equals 1 to infinity of the tangent of 1 over n diverges. We know that it diverges because it does the same thing as the series that we compared it to. The harmonic series diverges, therefore this one diverges as well.